Welcome. We're taking a look at lesson 11.5, which is confidence intervals. But before we do that, let's review two problems over the central limit theorem. So first off, we have a problem that says the average cost of a gallon of gasoline in a U.S. city is $1.75. You can tell it's not a current problem anymore with standard deviation of 13 cents, which basically means that over 60% of values will be either 13 cents less or 13 cents more. If you look at those gallon of gasoline prices, that would have over 60% of all gas prices. So here's the mean, which we use mu, $1.75. And the standard deviation is represented by sigma, 13 cents. It's kind of the idea of how far prices are separate from one another. It says if a random sample of 25 gas stations is surveyed or selected, whoops, let me rewrite that again, 25, there we go. Find the probability that the mean of the sample will be between $1.65 and $1.80. And again, the way we wrote this is we'd say the probability is between $1.65. That means it could be equal to. Oh, well, actually, between typically does not mean equal to. I'm sorry. Let me change that. So $1.65 is less than X, which is less than $1.80. That's what we're trying to solve for there, the probability. So to do so, I'm going to go to the central limit theorem. And what we found out is the mean of the population is $1.75. The standard deviation is 13 cents. We have 25 samples, and we want to know the sample, what is the probability of the sample mean being between $1.65 and $1.80. So I'm going to first put in here the mean of the sample at $1.65 and get our standard error value. And not only that, what's more important, oftentimes would be the Z value if you're going to go off of that. So here we are looking at this value, and the Z value is now appearing is negative 3.846. So what I'm going to do with that, what we learned last time, is I'm going to come over here just so you can see the distribution. I'm going to type in the Z value in right here. So we want all prices in between the Z value 3.8461538. I'm just going to stop there. And let's find out the maximum now. We want to know the mean or the maximum mean value of $1.80. And so I'm going to come back over here and put $1.80. Standard error is still the same value, but this time the Z value would be a 1.92. That would be the maximum. So let's go type that in, 1.9230769. And we're getting pretty well that this will, we have a 97.3% chance of having a probability in between $1.65 and $1.80. So 97.3 would be the correct answer here on number one. Number two, a website conducted an online poll where it was determined that 20% of stay-at-home mothers were working part-time from home. Find the probability that out of 45 randomly selected stay-at-home mothers, at least 10 and at most 20 were working part-time. So a couple things about this is one, this must be binomial because they're saying there's like two options. You can either 20% stay at home or working part-time, I should say, which I could just say 0.2, but I'll leave it as 0.20. And there's also another value. There's a binomial, means there's two options. That means if 20% were not, that means, or were, it means 80% are not working part-time, which would be a 0.8. For the record, my wife, this would apply to her, she would be part of this 20%. Now it says find the probability that out of 45 random selected stay-at-home moms, at least 10, that means you could be equal to 10, and at most 20 were working part-time. Now, when we do a binomial approximation, there is a conversion, which we talked about last class. And what I'm going to do here is I'm going to go down to this normal approximation, type in our values. We said that n is 45 here, and I'm going to turn this one off for a moment. The probability is 0.20, and so this automatically came up with the probability of failure at 80% or 0.8. And now we have this binomial distribution. We want to look at what's the probability that at least 10 and at most 20, which we would think the answer is going to be 35 0.5, which would be A. But this is not exactly correct because there is this conversion that we need to go over. If we can be equal to the value, so not just, let me write that out here. We're looking for the probability that we have at least 10 and at most 20. Now we have a correction factor that we need to come up with for this probability. So I have it right here on the left, and just kind of remind you that binomial, we need to come up with some, so let me refresh here. Let me pause and explain this to you. What's happening here is this is the normal approximation, and it has it, what we would, if you look at this, this is a continuous curve. Continuous is the word I was looking for there, meaning there's no breaks. But binomial, the truth is you can't have like 4.5 people saying something, or 4.5 would be somewhere in the middle here, or 5.5 people, something like that. And so we need to really adjust this to make sure we involve the right amount for the probability. And so the binomial adjustment actually coincidentally involves a decimal. And so it's kind of strange, but this is the way it works. And so if you're saying 10 is less than or equal to X, if I come over here, this is it's basically the same thing, just written the other way. X is greater than or equal to that number 10. What you would need to do is subtract the 0.5. So truthfully, the probability that I would be looking at, let me write it out, one full time, it would be minus 0.5 is less than or equal to X, which is less than or equal to. And now less than or equal to the number 20 means I need to add 0.5. So 20.0.5. And so the probability here for a binomial approximation would be the probability that 9.5 is less than or equal to X, which is less than or equal to 20.5. That's actually what I need to calculate here, which will increase the amount of shaded area. And it also increases my number up to 42.6%. And so that would be my probability. We went from A to B just by increasing our probabilities, and that is the binomial distribution correction factor. That's what that was. Correction factor is what I need to say here. Well, 11.5 is going to deal with confidence intervals. And so what we're going to do is use normal distributions and a thing called a t-distribution to find confidence intervals for the mean, which we'll learn as we go. What that's referring to is basically what type of confidence could we establish for a mean being wherever we believe it to be. And so there's a whole lot of vocabulary terms that we might see today, some of which we've seen before, some like critical value, for example, but others will be new to us, some parameter we've seen before as well. So first, the maximum error. The maximum error, you might remember the standard error last class was the sigma with the and smaller notation here of the sample mean symbol, which is the X bar. Well, maximum error is when you take your Z value and multiply by that standard error. And so here is that formula that we had for the standard error. It was the standard deviation divided by the square root of samples. And so there's our first formula here, the maximum error. And I will show you on this calculator. Let me just refresh it over here that you will see these values as we go today, and the confidence interval that you'll see that value right there as we go along. Okay. Number one, it says a fire truck, a manufacturer has determined based on a sample of 80 trucks, that one model truck will allow firefighters to spray a stream of water on average 40 yards. The standard deviation of this measure is thought to be 6 yards. Use a 95% confidence interval to determine the maximum error of estimate for the distance water can be sprayed. Okay, so let's talk about what we have here. We have number of samples being 80. We have a mean of 40 yards. Whoops. Mean of 40 yards. And we have a standard deviation of 6. Now we want to have a 95% confidence interval. All right, so now what do we do with that confidence interval? So what we're going to use is this value A. So A can refer to a lot of different things, but specifically what we're going to use A for today is going to be the outside of the confidence interval. So the outside would mean it's the portion that is not within the 95%. So you could think of it as saying 100% minus the 95%, which will be 5%, but the way we'll type it in the calculator is we'll say that A equals 0.05. So that's what I'm going to do here, 0.05. And the tails, we'll get into that, but for now, just leave it at 2. And so what's going to happen here, let me plug these other values in. We have 80 samples. And let me just shrink that just a bit here. And there's our mean is 40, and the standard deviation is 6. Okay, so when I do this calculation, the maximum error according to the calculator is going to be 1.31, and we're going to see what the confidence interval is. Okay, so on this particular problem, the confidence interval, the way you would write this, is you take this value, which is 38.69. I'm going to go to the nearest hundredth, is less than or equal to the mean, which is less than or equal to 41.31. So we can say with 95% confidence that the mean is between these two values. I know they're saying they think it's at 40 yards. We can say here with 95% confidence it's within these two numbers, somewhere in there. And the maximum error, here they gave a capital E. The maximum error is going to be 1.31. So really what this is it's 40 minus that 1.31 and then adding that 9.31 there. That's how you come up with that value. Now, what was the math involved? Well, you take your Z number, which just to remind you how you get that, it's the quantile function here. And so what you would be typing in is the normal distribution with a mean of 0 and a standard deviation of 1. Ignore these numbers. It's just to get our quantile number, you go off of that. And then the quantile function, what it does is it finds out the area that's going to be on the outside. That's why I have the 1 minus over here. This will get us back to the 95% basically. And so when not that we have a graph here, this is going to find that 95 divided by the 2. What we're going to have here is it's going to find the far right area of the last 2.5% of the graph. So if you had the graph here, it'd be the last 2.5% on this side. And that's what it comes up with the Z number, which means that this Z number is what gets plugged in right here, that 1.96 basically. And it's going to multiply times the standard deviation of 6 and then be divided by the square root of 80. And that's how you come up with that number. Okay. So that's the math behind it. Now, so for you, you can just do it like I did the first time, just using my calculator, come up with the numbers that you would get for this particular problem. Stop the video if you need more time. All right, example 2. Let's now talk about this confidence interval. So this is what I ended up writing on number 1 is I gave a confidence interval. And I didn't really label it. I should have. This would, let me come back here and label it. This is the confidence interval right here, confidence interval. And this is what the formula on example 2 is asking for. And this right here is the maximum error. Okay, so now on example 2, here is our formula that the confidence interval will equal that mean, the mean of the sample plus or minus the maximum error. And again, here they just substitute all that in there. Okay, so let's look at the second problem. It says a company gives a 4-hour boat tour for Dolphin Watch. On 30 tours, the time between the first leaving the dock to a sighting on a dolphin averaged 125 minutes. Assume a normal distribution with a standard deviation of 28 minutes. Find a 95% confidence interval for the mean time until the first dolphin sighting of all tours. Okay, so here we have 30 tours. Let's say N is 30. The mean is 125 minutes. And the distribution has a standard deviation of 28 minutes. So we want to find a 95% confidence interval for this mean. Let's see, what can we state with 95% confidence that the true mean will be in between? And so what I'm going to do is I go over here to confidence interval. And since it's 95, I should label this on each time, the A will equal 100% minus that 95%, which is 5%. So A equals 0.05. Okay, so when I come over to my calculator, I'm still going to have A as being 0.05, but now I'm saying the mean is 125 minutes. My standard deviation is 28 minutes. We have 30 samples. So my maximum error is basically 10.02 minutes, which puts our confidence interval. You take this and you would add, subtract and add that 10.2, and that's what's calculated right here. That our confidence interval is, we can say with 95% confidence that a tour will see have a dolphin sighting between 100 and basically 15 minutes and 135 minutes. We can say that with about 95% confidence. That's my confidence interval there. So I'll write that out. Confidence. Oops, that doesn't look like. Let me try that C again. Confidence interval. So, like I said, we can be 95% confident that the true mean will fall in between these two values. So now here's one for you to try, and it looks like I should be using not equal to, but just less than signs like that. Here's one for you to try. Pause the video if you need more time. Example 3. A city manager is preparing a report on recycling efforts. She finds the daily total weight of the recycled materials for 30 randomly selected days of the year. So that's going to be our N right there. N is going to be 30 days. These weights are normally distributed with an average weight, so this is the mean, of 22,500 pounds and a standard deviation of 11,100 pounds. That's a large standard deviation there. Find a 90% confidence interval. So if my confidence interval is 90%, then my A is going to be 100% minus 90%, which equals 10%, or you could say A is 0.1 or just 0.10, whichever way you want to look at it. I'll just do it 0.10. It says find a 90% confidence. Okay, so let's come up here. We want A to be 0.10. We have a mean of 22,500, standard deviation of 11,100, and again, 30 sample size. This means the maximum error, for this particular data would be that 3,333 pounds off. I'll do 0.42. Actually, on this one, I'm just going to round it to the nearest pound since we're talking about such large pounds. And so our confidence interval is from 19,166. I'm going to round to 7 to 2,000 or 25,000. Sorry, 25,833 is where the mean would be located, which is a huge difference in these numbers here. It's very, very large. Now, I'll let you take a look at this problem. Now let's take a look at the t-distribution. So some things about the t-distribution that you need to know is it's bell-shaped just like the normal distribution. It's symmetric about the mean. The mean, median, and mode equals 0. So not only is it symmetric about the mean, it's symmetric at 0 in the very center of the graph here. The curve never touches the x-axis. The standard deviation is greater than 1, and the distribution of family curves is based on the sample size. As n increases, the distribution approaches the standard normal distribution, like the normal with a mean of 0 and a standard deviation of 1. So as n increases, it gets closer and closer to the normal distribution. Okay. So using confidence intervals for the t distribution, you basically have the same formula. The only thing different is instead of using the maximum error, which is the z value times the standard deviation divided by the square root of n on the number of samples, you're going to use the t value. So instead of using, let me scroll over here, the z value, it comes from the normal distribution, we'll use the t value from the t distribution. We use this when the sample size is less than 30, by the way. T is a critical value with n minus 1 degrees of freedom. That's going to come into play later, okay? It's always the sample size minus 1 degrees of freedom. So here is our problem. It says, the owner of a Labrador Retriever wishes to enter his dog Max into a competition. Max retrieves a fake bird 25 times at the same distance. So notice my samples here, it's 25, which is less than 30. So that's why we're going to use a t distribution. Let's see here. It has a mean. The owner times Max. It finds the data is normally distributed with the mean of 18.4 seconds. 18.4 seconds. And standard deviation of 4.7 seconds. Find 95 or 90% confidence interval. So again, A is going to equal 100% minus 90%. And this is a good little diagram to show you why or what's happening with the tails. This has two tails of information, 5 on each side. And so though A is actually 0.10, we're going to treat it, when I go in the calculator, it's going to be divided by that 2. And that'll give us, so we'll be looking at the values at for the 95%. The 95 percentile and over, and the first 5 percentile. That's basically what's going to happen. So I'm going to come over here. And again, A is 0.10, and we have 2 tails. I come down to our data. We're going to say the mean is 18.4. The standard deviation is 4.7. What's going to happen differently is we're going to say we have 25 samples. Notice the z value goes undefined, and the t value now has a number. Now, why does it have a number? That's because you use the t distribution if you have less than 30 samples. That's just kind of the rule. If you have less than 30 samples, you need to use the t distribution because that deals with how many degrees of freedom. Degrees of freedom just mean unknown variables. If you're over 30, we have a pretty good idea it's going to be very similar to the normal distribution because that's what this approaches. As the n increases, it approaches the normal, and so we'll just use this. And so that's why if you look at the very end of my calculator when I programmed it, this only works if the samples are greater than 30, whereas this one only works if this or greater than or equal to, I should say. This one will only work if the samples is less than 30. And so we have our t number. What is that saying? This t value, remember the t distribution is centered at 0, according to that previous chart. There's the 0. This t value right there is 1.71. 1.71, which means this one would be negative 1.71. That's the t value there. Okay, so having said all of that, if we come down here, the confidence interval would be created. I know this isn't the maximum error. That's not what we call it. That's with the z number, but the value is, well, I don't have it shown. I need to add that in there. You might see what we're adding each time, but the interval would go from these two values. So what will we have? Between 16.79 seconds is less than the mean, which is less than 20.01 seconds. We can say this with 90% confidence. So one thing I want to point out is if you want to have more and more confidence, if you want to get higher and higher, you would have to widen out the amount you're taking. So 90% goes basically from here to here. If you wanted to have more than 90%, if you wanted to reach more, your interval is going to increase. So watch what happens. If I change my A, let's just say to 0.05, what's going to happen is this value is, notice it's a little smaller. This one's a little bit larger, which increases the overall interval. just the opposite. Let's say we only wanted to find the top 80 or the inner 80%, where we could say with 80% confident of the mean, the interval will get more and more narrow. So if you want to be more confident, so let's just say 99% confident, I would do 0.01 because that's 100% minus 99%. The interval itself will get much wider because it's allowing for more answers, so we can be more confident of the true solution. All right, with that kind of background knowledge, now I'll let you try example 4 GOL. Pause the video if you need more time. All right, now let's finish this lesson up with the minimum sample size formula. The minimum sample size needed when finding a confidence interval for the mean is given by this formula, where n is the sample size and e is the maximum error. So if we're using maximum error, we're dealing with the z, or the normal distribution here. And so this will tell us how many samples we need to have, the minimum number of samples to give us a true number here. So it says this. Medical equipment manufacturer requires that its measurement tools error, I know it looks weird, but that's error, no more than plus or minus 0.01 milliliter with 99% confidence. If our standard deviation is 0.05 of a millimeter, how many measurements are needed? So let's write out our value. Here's what we know. The A value is going to equal 100% minus the 99% confidence, which is 1%, or we could say A is 0.01. And we want it to error. We want the error to be no more than 0.01 plus or minus, but I'm just going to put it that way. And also we have this standard deviation of 0.05. Okay, so what I'm going to do is I'm going to come over here to my calculator and plug in these values. The first is the alpha is 0.01. Okay, we have that in there. Great. We don't know the mean, so I'll just delete that. The standard deviation is 0.05. We don't know how many samples we have, so I can delete that. When I come over here, I need to also input my error, needs to be 0.01. When I type that in, this tells me right here the minimum sample. What it does is it takes the z value, again for the 99th percentile, what the z value would be. It multiplies it by the standard deviation, it divides it by that error, and then squares the whole value. Our answer here is that we have a minimum. We need at least 100, and I'm going to say 66 samples. So truthfully, we'll usually be rounding that to a whole number, because if it's a sample size, usually we count wholes. I don't know many samples that you could have, like 3.5 samples, but for the most part, that's a whole number. And so I'll say at least 166 samples. And so the math in there, if you're wondering, wait, what just happened for the math, is to find that minimum, which the variable they use is n for samples. What you do is you take your z value, you multiply it by the standard deviation, and you divide it by the error, which they gave us. That's a z there. They gave us 2 of those values. What they did not give us that would be squared and squared. What they did not give us is the z value, and that's the quantile function. That's what I was talking about up here, or it's the normal distribution's quantile function. And so that's basically what happens right in here. And it calculates that value for us. Now, this one's not showing us the number. That's because I programmed that one specifically based off of having samples. But notice how this is a different letter here. It's not Z, CI, it's just the Z. And so it's being calculated down in here. There it is right there. It's getting calculated, and the Z value on this particular problem for 99% confidence would be 2.5 57, 58, 29, so on, so on. So that's the math that takes place right there to get that 166. All right, with that, you have a problem. Pause the video if you need more time, see what you come up with.